Hello everyone, so in this video we're going to go ahead and draw the three appropriate Lewis structures for the given species below. So that it's going to be C4H8O. So first we need to go ahead and calculate for the degree of unsaturation. So we have a formula for this. So we have half times 2C plus 2 plus N minus H minus X. So let's kind of break this down. So for our C here, that's going to be our carbons. Our N here represents our nitrogens. Our H represents our protons or hydrogens. And then lastly, our X is going to be all of our halogens. So using the degree of unsaturation formula that we have just written out and applying it to the given molecular formula of C4H80, we can go ahead and find the degree of unsaturation for this molecule. So again, we have half times, let's see here. So for C, again, that's carbons. We see here in this formula, we have 4 carbons. So add that in, plus 2 plus N. We don't have any nitrogen, so that's 0. For our H's, we have 8 H's. So we'll put the number 8 here. And then for all of our halides, we have 0. All right. So now we can go ahead and put everything into the calculator. Once we do so, we'll get this to be equal to 1. So the given formula or molecular formula corresponds to a structure with one element of unsaturation, which can be a ring or a double bond. So to draw 3 appropriate Lewis structures for the given molecular formula of C4H80 or O for the oxygen, we first need to determine the total number of valence electrons that corresponds to the given formula. So let's go ahead and calculate that as well. So starting off with our carbons here, we see that we have 4 atoms of carbon. Each atom of carbon will give us 4 valence electrons. So 4 times 4 is equal to 16, so we'll get a total of 16 valence electrons coming off of just our carbons alone. Moving on to hydrogen, we see here that we have 8 atoms of hydrogen. Each gives us 1 valence electron. So 8 times 1 is equal to 8 valence electrons. Next we have oxygen here. Oxygen, we just have 1 atom of oxygen. Each atom will give us 6 valence electrons. So that equals to 1 times 6 is always just going to be itself, and that is 6 here in our case. So we have 16 coming off from the carbons, 8 coming off from our protons or hydrogens, and then 6 coming off from our oxygen. All right. So second step is going to go ahead and draw a appropriate sigma bond framework. So 3 possible sigma bond frameworks with 1 element of unsaturation is going to be possible. So let's go ahead and draw this out. So we'll draw all the bonds here. So we have a CH3 at the end. And we can see here again that this molecule needs to have 4 total carbons. Each carbon likes to have 4 bonds, so it is usually sort of a central atom. And lastly, we have our oxygen still and 1 carbon left, as well as 1 proton. So we'll have carbon, double bound oxygen, single bond proton. So that's one of our sigma frameworks here. Next, we're going to go ahead and actually make this molecule into a cycloalkane. So we have a cyclic single bond molecule here. Again, we have 4 carbons total. All right, and because we need to use up all 8 protons as well as having carbon liking 4 bonds, we'll go ahead and add 2 protons per carbon. All right, so we've completed the cyclic version of this molecule. And lastly, we're just going to go ahead and sort of do the one that we did in the first, except we're going to go ahead and add or put our carbonyl group into a different area. So we have we have a carbon at the end connected to 3 hydrogens here. And of course, like we said, carbon's always just going to be a central atom. So we can do a carbon double bound oxygen here in the second carbon. Now, of course, we have 4 carbons, so I'll put the other 2 here. And of course, just fulfilling its octet with all the leftover protons that we still have left. Alright, and third is just to basically complete our octets using lone pairs. So all of our hydrogens are happy because of the duet rule, all of our carbons are happy because of the octet rule, but the oxygens here in our case still are not satisfied yet. So oxygens like to have 2 bonds and 2 lone pairs. So for our carbonyl group, which already has a double bond, we're just going to go ahead and add 2 more lone pairs. Now for our cyclic oxygen here, this one has 2 bonds as well. Instead of double bonds, it has 2 separate single bonds. And then again, we just need to go ahead and add 2 lone pairs. So that right there, these 3 structures are going to be my final answer for this problem.